Okay, hello, welcome back. So let's begin studying the rotational kinetics of rigid bodies. So just let me quickly go back to a little bit of reminder. So for translational motion, we saw F was equals, let me do it this way. Force, it was proportional to, this is a proportional sign, to acceleration. And the constant of that proportionality was the term we called it mass or inertia. As the inertia changed, the relationship between force and acceleration changed. That was the translational form. We should expect a similar inertia effect in the rotational domain as well. You can visualize or think of a bigger wheel is harder to turn than a much smaller wheel. So there is that notion of inertia in rotational domain too. And that is what we call moment of inertia. Well, the name suggests moment of something. If you remember, it was kind of the rotational effect of that thing. You had moment of a force. We had moment of linear momentum. We called it angular momentum. We had, all sorts of moments. Here we have moment of inertia, which is kind of rotational equivalent or effect of inertia in rotational domain. Okay, let's see what it is. I will start with a very simple example. Assume right now a particle. This is just a particle with some mass m and some distance r from a fixed point. So in this case, my mass is going around a circle. And I have a force F acting on it, always tangent to this path or perpendicular to the massless link. Let's study motion of the system. I know that in the tangential domain, tangential axis, forces in tangential equals mass times tangential acceleration. So my entire force, the only force, is in tangential domain. So I can write it as F equals this mass m times tangential acceleration. We just saw in the previous chapter that the tangential component of acceleration, we can write it as distance times alpha in the case that you're rotating about a fixed point, which is our case. So force equals mass times this term, r times alpha, and alpha is the angular acceleration. Let me make it more curved. This is alpha, is angular acceleration of my system. One other thing I want to add here, I'm looking for rotational domain terms. So I have force. Force is in linear domain. The rotational equivalent or effect of that is moment. And moment of a force, let's call this point O. About that point O is the distance times the force. Because they are perpendicular, we just multiply the sizes. And I substitute F here. So R times F from above. I write it as mr alpha. and I simplify everything, it becomes mr squared alpha. So on one hand, I have, what happened? This is angular acceleration. This is my angular, let's call it angular effort. We call it moment, but for the sake of comparison, let's call it angular effort. So angular effort equals mr squared alpha. Note that your effort equals a constant times angular acceleration. And this constant is what we call moment of inertia. Moment of inertia. And we usually use letter I for it. So moment equals I alpha. Let's call it IO. So we have this equivalent of equation of motion. Instead of F equals mass times acceleration, we have moment equals moment of inertia times angular acceleration. And this proportionality constant is moment of inertia. So mr squared. I went through all of this to show you where the concept of moment of inertia come from. Obviously, the systems that we'll deal with, we need more general ways to calculate and reason why these terms exist. But the simple example showed the concept. Let me clean up here and move this here. Okay. Oh, my A was left out. Okay. Oops, where did it go? All right, now imagine a different scenario. I have a little bit of this mass m. Instead of being, what is happening? Instead of being some mass, it is a tiny mass, dm. So I add all these little tiny d's here, here. All of it work out. Now a rigid body is essentially a collection of all these little dm's. So when you calculate the moment of inertia for a rigid body, so for a rigid body, which is a collection of a whole bunch of little dm's about some point O, you can calculate the moment of inertia about that O by adding all these little dm r squared. So these terms, you can add all of them together, and it takes the form of integral. It is r squared dm, where dm is here and r is the distance from your reference point to that little particle in the body. That's how you calculate moment of inertia. And when you have it, you can relate the moments of forces to angular accelerations. We'll see in more details how in the next video, in the next videos. But for now, the whole point here is the definition of moment of inertia. What else did I want to say? I leave a whole bunch of little remarks and tricks and information about moment of inertia for another video. But I think for now it's suffice to say that moment of inertia, that is the equation you calculated, but noting that moment of inertia is the rotational effect of all the inertias in a body. Okay, good. Oh, one other way to word this. Inertia is the property of a body that resists linear acceleration. Moment of inertia is a property of the body that resists angular acceleration. That is another way you can think of it. Okay, so I'll stop here. And in the next video, we cover a few properties of moment of inertia. So I'll see you then.